Hello. Reliable, affordable electricity is a hallmark of virtually every strong economy. You've joined the Chartered Institute of Ergonomics and Human Factors event platform. Today, we'll be taking a fascinating look back and a telling look forward into how electricity is generated by nuclear means in the UK and how Human Factors has played its part in that journey over the last 80 years. This session has been produced by members of our Nuclear Sector Group, also known as Nuclear Special Interest Group, or SIG, led by John Lovegrove of Canary Designs. John has a long association with the group and with the Institute, and we hope this event might sharpen your appetite to contributing to the work of the Nuclear Sector Group, which is actually led by Christian Wilhelm in the future. You'll be hearing an introduction from John very shortly. I'm Steve Barraclough, your facilitator for today, and I'm delighted to be alongside members John, Ned Hickling and Andrew Chadwick of Cavendish Nuclear, who comprise your panel. Now, our format today is a little different to that you may be used to, and it's useful, I think, if I just summarise it here. Due to the amount of material our panel would like to put before you today and the expressed desire of the Institute and its audience to keep these sessions as concise as we can, then our event falls today into 4 parts. Between each part, there will be a live comment and discussion from our expert panel, and we conclude with final comments and the possibility of some questions at the close, depending on time. Which will be in around about an hour and a half, up to a maximum of an hour and 50. So bear with us, please. There's plenty of fascinating material to cover. As many of you all know, you can use the chat function to say hello, to comment, or to pose questions at any time. Our panel may be able to get to your question in chat, so please look out for any answer and please be patient on this. But let me say at the outset that we do have a good deal of ground to cover, and probably the sense I have is that the scope for questions today will probably be less than you might usually expect. Okay, please, just as a reminder, please accept that everything that goes into chat will be seen by everyone in the room and by a much wider audience in addition who view the recording. So please keep your input respectful, professional, inclusive, and as free of jargon as I know you will, as I know you would expect in a public forum where there will be differing levels of knowledge about our subject. We'd like to also encourage the development of questions that may go unanswered today via our excellent member community facility that you can access via MyCIEHF. Go to ergonomics.org.uk/get involved/nuclear sector group, and you'll see all about the group and how to get involved. Now, practically, if you happen to experience poor sound or impaired vision today, then please do first check the operation of your own device, your network connection, and in particular your sound source. Leaving the room by closing the browser and returning is often a simple way to fix everything, so please try that if it turns out to be, as it often is, a local issue. If there is a general issue affecting everyone, and heaven forbid we don't face that, then please let us know in chat and I'll do my level best to try and fix it. I'll keep you updated also if that happens, so please look out for chat. Okay, so let's settle back and we'll begin our journey. Just to underline that the Institute is making its platform available today for this event to the group, and the views expressed today are the personal views of the individuals within the group. This event is focused on the UK nuclear generation sector. Now, before you hear an introduction from John, we'll see a short video based on data from energy company BP that actually gives us a bit of context and puts the UK situation in context over the last 50 years or so. This video compares how much power has been generated annually by nuclear means by nation since the mid-1960s, since 1965 in fact. So look out for the UK in the animation. Straight after that, we'll hear a short introduction from John, and after that you'll hear the first part of 4 presentations recorded as personal viewpoints by Ned Hickling. At the close of each presentation, I'll be inviting our panel to comment on what they've just heard from a human factors perspective. But from a layman's perspective, it'd be wrong of me not to whet our collective appetites with a bit of a sense of the thrust of each of our 4 presentations today. And in broad terms, they are, to give you a little idea, as follows. Part 1 focuses necessarily on context, on the early days, and the drivers behind the nuclear power program. Part 2 acknowledges a period of very significant growth and learning. Part 3 will look at a period of crisis, challenge, and consolidation. And finally, part 4 will consider the new millennium and asks, where to from here? So, with that in mind, settle back and let's enjoy our first video.
Welcome to the NESIG 2021 webinar series. This afternoon we will be covering the history of human factors involvement in the UK nuclear industry. Having survived the millennium bug, I graduated from Loughborough University in the summer of 2000 with an ergonomics degree. Ergonomics covers anatomy and physiology, cognitive psychology and how we perceive the world, the influence of the environment on our performance and ability to perceive the world, the influence of design on our performance. The course provided us with the necessary skills to turn the theory into practice. We were taught how to go out and measure human performance in the field, and then how to model it up and present it for a wider audience. Reflecting one of the key skill sets was our ability to integrate with multidiscipline teams. I started my career in manufacturing systems engineering for Airbus. I then joined a large engineering consultancy where I was taught how to integrate human factors into large infrastructure projects. It was my first Introduction to Nuclear Projects. I formed Canary Designs in April 2011 with the specific purpose of creating a company that could model up human interactions, whether it's with a 3D environment, so digital human modeling, or using simulators of control screens. By bringing it all together, it's possible to assess how people will interact with your design. I'd like to introduce Andrew Chadwick. Andrew is our safety case specialist. Andrew graduated from Swansea University in 1999 with a mechanical engineering degree. Since then, he's worked across the UK nuclear industry as a safety case author, leading multidiscipline teams, and he was the safety case owner for the NuGen Moorside project. He's currently working as a principal safety case engineer at Cavendish Nuclear, supporting Devonport and other major projects. I would now like to introduce you to our key speaker, Ned Hickling. Following an earlier career in the insurance and pharmaceutical industries, Ned read ergonomics at Loughborough University and graduated in 1981. For most of the next 5 years, he undertook research on behalf of HSE. He joined the Safety and Reliability Directorate of the United Kingdom Atomic Energy Authority in 1986, shortly after the Chernobyl accident, and reviewed the UK AEA case, why a Chernobyl accident couldn't happen here. He was quickly seconded and subsequently employed as a human factors engineer for the design and construction of the Sizewell B nuclear power plant. Here he was involved in design, input and safety assessment in a wide range of ergonomics issues, from control room design through to human-computer interaction and alarm system design, to the development of checklists for guards against cognitive or conceptual error in station management and maintenance crews. Since that time, he has undertaken human factors work in all parts of the nuclear fuel cycle, in both civilian and military projects, for new projects and safety reviews. Ned's presentation considers the role of the human factor and the influence of human factors professionals in the growth and development of nuclear power in Britain from the earliest days to today. In conversation with me, he pointed out he joined the nuclear industry about halfway through the story. He's asked me to point out that the recounting of events and their interpretation must be personal. Not only has the development of the sector been complex, but as you will see, the early years are somewhat cloaked in secrecy.
Thank you, John. We'll now turn to Ned's first presentation.
Hello, I'm Ned Hickling. I'm going to talk today about the role of human factors in UK nuclear power. This is very much a personal viewpoint for two principal reasons. Firstly, much of the early history is cloaked in secrecy, and secondly, because it is a complex picture, so what you get today is something of a simplification. The early years of nuclear reactors were not about generating electricity. They were really about meeting the perceived need for Britain to have nuclear weaponry, as characterized by this picture of V-bombers designed to deliver strategic nuclear weapons, predominantly towards Russia, and this picture is from 1953. During World War II, British scientists collaborated with the USA in the Manhattan Project on the production of the first nuclear weapons. After that cooperation ceased in 1946, and the UK government decided it wanted nuclear weapons in order to gain a seat on the United Nations Security Council, as well as for national security. At that time, this was achieved by scientists who worked at the newly formed Harwell and scientists at the Universities of Oxford, Cambridge, Birmingham and Liverpool. In order to have a nuclear weapon required the production of military-grade plutonium, and this was to be done at Windscale, a former munitions site up on the west coast of Cumbria. And initially we were going to do what the Americans did, have water-cooled and water-moderated reactors. In order to do that, that meant that the piles would have to be 5 miles apart from each other and 50 miles from major population centres. This is a constraint not easily met on a small and crowded island, and the Harwell scientists overcame this constraint and concluded that air-cooled reactor piles would be simpler and safer to operate than the US design. So early in 1947, about 5,000 workers at the peak began construction of the Windscale piles numbers 1 and 2, and this was completed in 1952. During the construction of the Windscale piles, Sir John Cockcroft visited the United States informally and learnt that uranium oxide particles had been found near the US Oak Ridge facility where their reactors were operating. He reasoned that as there were over 70,000 cartridges involved in the reactor cores, that there was at least a reasonable chance that one cartridge would burst. The management team at Risley took this risk calmly, it is said, and the engineers were unimpressed by this concern. However, Cockcroft and his fellow scientists persisted, and finally, following an intervention and a meeting between Sir John Cockcroft and Winston Churchill, it became necessary to fit the stacks that were built for the exhausted cooling air to be fitted with activated charcoal high-efficiency particulate filters. These were called Cockcroft's Follies. If you look at the picture, you can see squares towards the top of the two stacks. The reason why these filters were fitted so high up was, with the pace of construction, the stacks had already been built to about 70 meters before it was deemed necessary to fit the filters. From the commencement in 1946 until the mid-50s, it is estimated that about a quarter of the British gross domestic product was actually expended on nuclear projects, predominantly military ones. However, in 1953, the design for Calder Hall, our first electricity generating nuclear power station, commenced. This was actually intended not only to deliver electrical power, but also to be able to produce weapons-grade plutonium. Throughout the remainder of this presentation, I will highlight things in red where there is some human factors relevance and some notion of attention to human factors, particularly in safety. When Calder Hall was designed, there were some deterministic design principles. There should be redundancy, that is, there should be more than one system or system train available to deliver functions for nuclear safety. Those trains should be separated so that a catastrophic failure of one would not affect another. And of course, because it was there to generate heat, there was considerable thermal analysis to make sure that it would do that successfully, not necessarily with a high degree of efficiency, but nevertheless to generate heat and therefore electricity. However, there is no explicit record which considers the notion of diversity, that is, entirely different forms of system to meet nuclear safety functions, nor is there any explicit reference to the notion of human factors. However, it should be borne in mind that the so-called Ergonomics Research Society only was formed in 1949, so as a discipline, as professionals, we barely were known to exist. Nevertheless, by and large, it has been said by ergonomists who've worked on the design and operation of that control room, it seems to be pretty good. In 1954, the United Kingdom Atomic Energy Authority was formed, and in the Act of Parliament which allowed that formation, there was actually, interestingly, no reference at that point to nuclear safety. Calder Hall was constructed in 3 years at almost breathtaking speed. So by October 1956 it was on the national grid, producing electrical power and also producing plutonium. In contrast to the Windscale piles, which were cooled by air, Calder Hall reactors were cooled by carbon dioxide in closed circuits. This was used and believed to suppress fire, and that carbon dioxide would transport fewer radionuclides than air or water should there be any burst of a Magnox fuel canister. It's worthy of note that the plutonium that it produced could only be processed at B205 at Windscale from 1964 onwards. This was a time of nuclear euphoria. I've quoted what the Queen said in her speech when she opened Calder Hall. You could see the giant electrical meter in the bottom right hand corner, actually furiously cranked by a man behind the dial in order to make the pointer go round, and actually they'd already been generating electricity for 3 days. But never mind. This new power, which has proved itself to be such a terrifying weapon of destruction, is harnessed for the first time for the good of our community. And that enthusiasm was reflected by the Minister of Energy, Rab Butler, in the government, who said by 1965 every new power station will be atomic and the electricity will be too cheap to meter. However, almost exactly a year later, Windscale pile number 1 caught fire. How did this happen? When the reactor was critical, a phenomenon known as Wigner energy built up within the matrix of the graphite moderator which formed the structure of the core around the fuel canisters. This energy needed to be released, and this was done by overheating the core, running it above its normal temperature, their so-called annealing process. When this was done, there would be observed a sudden spike in temperatures as the Wigner energy was released as heat. However, this wasn't a well understood phenomenon, and no records were kept of the core temperature rise needed to release the Wigner energy on each successive release cycle. The fact of the matter was that the temperature needed to release the energy was rising on each successive release cycle. So on annealing on this occasion, a core fire started. This was the graphite burning and also the canisters of fuel burning. This went on for 3 days, and as workers continued to come in and leave the site, they could see brown smoke emanating from stack number 1, from pile number 1. Initially, it was attempted to put the fire out using carbon dioxide from the adjacent Calder Hall carbon dioxide supplies. This didn't work, and then after that the only remaining option was to flood the core with water. However, the temperatures were understood to be so high, they were off the temperature scales that could be measured. It was worried that putting in water would actually result not just in the release of steam, but in the dissociation of the water molecules to hydrogen and oxygen, with consequent explosive recombination. 3 fire tenders fortuitously could be coupled up to ports, instrumentation ports on the top of the pile, and at the signal all 3 furiously pumped in water, and the fire then was consequently put out. There was an internal report, the Penny Report, executed to see what had gone wrong. However, this was a secret industry in times of high secrecy, and that report was not actually published until 1988, some 20 years later. So once finally released in 1988, what did we find that the Penny Report said? This, by the way, is available online, and I give a link in the bibliography at the end of the entire presentation to this. The response was prompt and efficient and displayed considerable devotion to duty on the part of all concerned. That can be taken as a considerable understatement. They stayed at their posts doing what they needed to do to pump in water, in the belief that there was a high probability that the entire pile would explode, but there were no other options available. So the measures taken were adequate. There was no immediate damage to health or any of the public or of the workers at Windscale. However, as I grew up in the Lake District at that time, I can tell you there was no school milk for a couple of years because of the radionuclides that landed on dairy farmers' fields. The report was critical of technical and organisational deficiencies, and more detailed assessment was needed to get organisational changes, clearer responsibilities for health and safety, and better definition of radiation dose limits. So that's telling us that we didn't really understand the nuclear phenomena terribly well at that time, but it's also telling us something else, that really the notion of the need to pay considerable attention to nuclear safety wasn't well defined, and you will notice from the description I gave you before that there was no concept of the idea that there could be a file, so they were in fact making it up as they went along. Shortly after the fire occurred, Harold Macmillan, who was then the UK Prime Minister, was in talks with the USA about renewing nuclear collaboration and indeed collaboration on military intelligence. Dennis Toohey, who was the deputy manager at the time of the fire, later said in a Telegraph interview in 2008 that the officials who told the US about his staff causing the fire, the politicians were, a shower of bastards. In other words, it wasn't anything to do with any national competence or incompetence, it was all down to the people running the facility. A theme that actually returns in Chernobyl. However, it is important to note that the fundamental underlying causes from the fire, i.e. the limited understanding of Wigner energy and the lack of preparation for accidents, were not explicitly stated. If it was a cover-up, it was a cover-up by being an internalised report and by arguably pulling punches, or at least that's what we'd say in our modern perspective. But the really important thing to note is that without Cockcroft's follies, those filters up the stack, this accident would have been Britain's Chernobyl. As it was when the Chernobyl accident happened, there was some initial hesitancy to recognise that an accident had happened in the Soviet Union because there was still evidence of radionuclides available in grass and pasture surrounding the Sellafield plant. And of course the Chernobyl accident was enunciated initially in the UK by alarms going off at Sellafield. I will stop at this point for the first part of the discussion.
Ned, thank you for that very interesting insight into the first part of the development of nuclear power here in the UK. Let me invite our panel now to live their mics and join me here on the stage. And John, can I turn to you first for your reaction to what we've just heard?
Yeah, it was. It's amazing, really, how it started when you go through the 1940s, and how experimental the nuclear industry was, and then just quickly going towards the end, the findings in the Penny report, I think can still ring true today. You know, if you look around you, that's my contribution. So over to you guys.
Andrew?
Okay, yeah, I think it's fascinating seeing where we've come from. And like when John was saying that whole, it's been birthed of a scientific endeavor from a national requirement. And it was a different world, you know, just coming out of World War II, going into the Cold War. It was a completely different world. But there was two things that really struck me there. One was the fact that even though processes and procedures weren't in there, it wasn't without consideration for ergonomics and human factors and safety systems and all this kind of stuff. And you know, I've spent a bit of time at Sellafield. I think most of us, you know, been in that sphere of seeing the Windscale chimneys, and it's always struck me from day one, you know, why put the filters at the top? When I heard about Cockcroft Follies, and he sort of empowers you sometimes, because sometimes you can be put in a box of saying, oh, you know, this is nonsense. Why are you whinging about this? It's not really helping. But to see the integrity of somebody who actually had to get, you know, the Prime Minister to intervene, to put a safety system in place, and then that's what actually mitigated something, you know, unthinkable, really. It empowers you to really, on that day-to-day basis, really drive down to the answers that you need to do. So, yeah, quite a story.
Here is certainly an industry that patently lends itself to what human factors can bring. And I think we've heard, given the military thrust and the level of secrecy around the establishment of nuclear generation, this was a complex time. I guess also, as Ned mentioned, that ergonomics in the UK in the form of the Ergonomic Society only came into being in 1949. So its impact on any industry, let alone the nuclear industry, would have been in its infancy. So it's a fascinating glimpse, I think, into what is patently a very complicated industry involving thousands of people doing quite complex things.
Yeah, I was surprised by the build time for Calder Hall, when you think that it's gone from, you know, concept to fully functioning in 2 years. When you're looking at the installation, commissioning, and you compare that to modern day build and design processes for modern day nuclear plants. Yeah, that's unbelievable.
Yeah, and it wasn't just the design they were developing the materials and the manufacturing techniques at the same time in parallel. So a staggering achievement. But like you say, that root of it being a national need based on, you know, on a scientific endeavor. To see it now, you know, we started, I think on John's introduction there, we were talking, myself and John were at 99, 2000 starting. It's a fully formed industry by then. So seeing the roots of it here, it really is quite staggering. And the first video shows how early we were in the development of this science as well as a nation. So this was very early on.
I can see in chat that Joe is saying the picture painted feels unrecognisable today, and I think we all recognise that that's the case. But it's not difficult to understand, is it, that the prospect of very cheap power, very cheap reliable power for an economy just coming away from war, and in an environment in which the development of nuclear weapons was prized, you can understand the impetus behind this industry and why things were done at such an incredible rate, it would seem to me, at least.
Yeah, I think just hearing what Ned said about the percentage of GDP that was spent on this program is utterly staggering. Just hearing all the stuff from the budget today, it sort of gives you a feel for just how important it was to the nation at the time, and the attitudes and the situation. We're living in a different time, so it's not comparable. But yeah, it is unrecognizable today, but I think the whole context is unrecognizable to us as well.
I've just seen Bill's question come in. I'll repeat the question. Given the poor understanding of the science, how do you think human factors could have prevented the Windscale fire? If you look at the approach that we take as a discipline now, the fact that the operators were freestyling with the annealing process, as in they weren't collecting data and recording temperature data or any records, and it was more about intuition and feel, I believe that our discipline would have picked up on that as a potential risk and would have looked at, number one, recording temperatures, and number two, looking at systemically looking at the consequences of that process. Hope that answers your question.
Yeah, I think there'd be a large element of trying to pin down the key parameters to control, and the time you've got, and the margins, as well as the other engineered safeguards that have come together. From a safety case point of view, I'm looking at trying to make sure we integrate. If I put a safety system on there, I don't want to confuse the human that's involved. But then ideally, I don't want to trigger that safeguard in the first place. So I think we'll probably get onto it with some of the later presentations in terms of that way that we'd stepwise through, because there are still, certainly I see it myself, is you go into a new project, it could be anything, it could be a reactor, it could be a chemical process. You've got to go back to the same process and make sure that everybody on the project understands that. That's never going to be a perfect thing, but maybe that comes in some of the later presentations.
Yeah, and later on we look at allocation of function. Sorry, I'm reading another question. Yeah, in the next video, we look at the allocation of function and knowing where the human's responsibility finishes and the system takes over, and people's situational awareness and understanding of the status of the plant at all times is something that we'll move into.
Okay, to John and to Andrew, thanks for now. I think there's a question popped up there from John B that you both, a question and comment, you both might want to consider and perhaps reply to in chat as we go. But for now, thank you to you both. We'll be hearing more from you later. So if you'd like to mute your cams and mics, please. We'll now move on and listen to the second part of Ned's presentation, which focuses very much on a period of significant growth and learning.
Okay, now let's think about the swinging 1960s and the 1970s. This was undoubtedly the period of the fastest growth in civil nuclear power generation, although not necessarily the greatest contribution to the national grid. Nevertheless, today, some of the current fleet of nuclear power plants are those that were built certainly in the 1970s. At that time, there were two key players: the United Kingdom Atomic Energy Authority, whose shield can be seen on the left, and the Central Electricity Generating Board, the CEGB, whose logo can be seen on the right. Of course, the effects of the Pile 1 fire could not be kept secret, and the British insurance industry found itself confronted with a large number of claims from the aftermath of Pile 1 fire. This resulted in the 1959 Nuclear Installations Act, substantially changed in the 1965 Act, which required sites to have licenses and permissions, and the government supplied indemnity against any accidents, thereby relieving the British insurance industry of a risk which they felt they couldn't, their actuaries felt they couldn't quantify. This was also the first time that any nuclear legislation made reference to safety, and there was an obligation on licensees to report dangerous occurrences to the newly formed Nuclear Installations Inspectorate, but explicitly the Act, interestingly, was not applicable to design and construction. In the 60s, a fleet of Magnox reactors were built. Some were operated by the United Kingdom Atomic Energy Authority. These were ones which were intended to have a dual purpose, like Calder Hall, and the CGB operated the ones which were solely for the generation of civil nuclear electrical power. And you will see that the first station on the list, Berkeley, is almost 3 times the electrical capacity of Calder Hall, and so it goes on up to the Wilver Magnox reactor, the last one to be built, finished in 1971 at 490 megawatts electrical, almost a factor of 10 greater than Calder Hall. Each site, by the way, was built with 2 reactors. Very early on during that development of the Magnox reactors and their building, the UKAEA was already looking to the next generation and produced WAGR, the Windscale Advanced Gas Reactor. You can see the green arrow pointing towards the sphere. It's an iconic picture, and that actually is the WAGR reactor, and you can see pile 1 and pile 2 stacks in the background. When one looks at the Magnox fleet, one begins to see that there are in fact more and more references to high integrity systems design, redundancy, independence, segregation, lines of defense. These are all terms that were being used. Deterministic design principles were used. So, for example, if you needed redundancy to meet the needs for nuclear safety, it would be less than or equal to 3 redundant trains that were needed. But a debate began to occur. Is 3 enough? And the notion of diversity began to be thought about as well. Interestingly, not so much in UKAEA, which had Crown immunity and was able to maintain secrecy. There was more openness for the CGB. And there was also more concern, I think it's fair to say, about safety and engineering. And the CGB had quite a number of confrontations and run-ins with one of the 5 architect engineering consortia that were formed to build these Magnox power stations. In parallel with the construction of the Magnox reactors, some ergonomics was already going on. The really big challenge, the really big area of complexity was seen to be the knitting together of separate regional electrical grids into the so-called national grid, and how did you produce grid control room designs which would allow clear understanding of such a large geographically distributed grid to be understood. It's also said that there was cross-fertilization onto the nuclear power plant designs, but it wasn't explicitly linked to specific safety functions, and it isn't well documented, with one exception which I will talk about next. And so this is a picture of the Trawsfynydd centralized control room, probably taken, judging from the hairstyles, in the early 1970s. The chap you can see eating his lunch, and lots of evidence of human occupation, a large brown paper sack for waste printer paper, and somebody's overnight bag there on the left hand side of the picture. And I show you this control room because it is the first where there is clearly documented and published evidence of ergonomics human factors intervention. So what's this all about? Well, it's a network diagram, or some people call it a swim streams diagram, depicting what happens from the start of pulling rods right up to the point where the turbine and the generator is connected to the national grid to provide power. It looks at activities in the reactor building, activities in the control room, and activities in the turbine house. And this is an overview diagram for much more detailed task analysis supporting the examination of each of those separate nodes. This was published in the Human Operating Process Control in 1974, published by Taylor and Francis, references given in detail in the bibliography. But interestingly, it was actually undertaken by Reg Sell in 1963, who was then part of the CGV Operational Research and Nuclear Plant Design section. And it was being done because of concerns about the ease and efficiency and reliability of actually starting up the power station. And as part of that ergonomics intervention, there was a study on allocation of function. There was a study of the control room environment and interface design studies. And interestingly, there was a study of information display, what information needed to be displayed to whom and where. And this is underpinned by all of the task analysis that this swim stream diagram shows here. And some of you might be surprised to see that there was also a study on computer control. Yes, there were computers in control rooms for nuclear power plants in the early 1960s. And so throughout the 60s and the early 1970s we had the growth and completion of the fleet of Magnox reactors. And you'll remember that the advanced gas reactor prototype at Windscale was already up and running and connecting to the grid actually in 1962. Two advanced gas reactors based upon that prototype, but of much larger scale, were connected to the national grid in 1976 with build times of 8 or 9 years. However, 3 more were under construction and they took around about on average 13 years to complete. You can see some very major principal differences in safety. On the left we have a schematic for the Magnox designs where the boiler producing the steam for driving the turbine and generating electricity is outside. It's in a separate pod from the reactor, whereas when you look at the advanced gas reactor on the right you can see that the boilers, which actually could now produce superheated steam, was contained in a large concrete biological shielding. So safety is now clearly on the agenda and is writ large in the civil engineering construction of the design. The high integrity principles that had already been referenced in the slide about Magnox reactors continued to be applied, and in some cases the notion of diversity started to be applied as well. And in fact in the first design, which was completed but didn't go on the bar straight away, Dungeness B, that diversity can be seen in later changes to the design. And the nuclear installations inspectorate became more active and were challenging against those design principles, but the problem still remained for lines of defence concepts. How many things do we need to constitute a line of defence? When is that much going to be enough? In parallel with the build programme for advanced gas reactors in the UK, the USA had a equally rapid programme and comprehensive programme for the construction of boiling water reactors and pressurised water reactors, both using water as a nuclear moderator as opposed to the UK designs which continued to use graphite as the neutron moderator. In the early 1970s, the US Nuclear Regulatory Commission commissioned the WASH 1400 study. This was the first comprehensive probabilistic study which started to address, using numbers, putting it crudely, when enough would be enough. And you'll see down at the bottom of this table 6.3 that for 100 reactors in the US it was estimated that the likelihood of an individual risk of early fatality was about 2 in 10 billion. The public belief in that figure and the general perception has changed somewhat by the accident that happened at 3 Mile Island, Unit 2 in 1979. This was an accident that continued to evolve before it was fully brought under control for 3 days. And as a result of public reaction, the US President formed the Kemeny Commission, whose very comprehensive report came up with a list of fundamental changes required for nuclear power plant builders, the utilities procuring them, the role and the involvement of regulators, and then for the operators, their training, their management, the overcoming of complacency, the better display and promulgation of safety information, and much improved procedures which would address different accident scenarios that could plausibly happen, improvements in control and display ergonomics, and in ergonomics for control rooms more widely. Fortunately for the nuclear industry, the US military had commissioned and had published in 1972 by the US government the Human Engineering Guide to Equipment Design by Van Cotton Kincaid. This very substantial Bible of human factors guidance was taken and adapted and rapidly made available for the design and assessment of nuclear power plant control rooms and wider facilities in a nuclear power plant. So on this bombshell we stop for the second discussion.
There we go. Thanks to Ned for the second of our four-part presentation. John and Andrew, can I invite you to join me? There you are. Thanks for that. So we've seen a period of significant growth and some significant learning as well, by the sound of things, and the emergence of regulation and the disappearance perhaps of the level of secrecy that had previously shrouded the industry. Andrew, can I turn to you? Is that fair?
Yeah, I think when you look at regulation, or you look at legislation, it's there primarily to get the confidence of the public to come in, and you can see this shift, can't you, from the military program into the civils, specifically with the larger and larger, more powerful reactors. You know, everybody's seeing the benefits of that, as we're sort of seeing as we're trying to grapple with net zero at the moment. And to be able to take everybody along with the journey, I think, is a really important thing to do. And to know that not everybody can eat. I think one of the comments is, we don't have to understand the nuclear physics, but we have to ask the right questions. It's one of the comments, I think it's John Berman put in there. That's absolutely right. And that's what the regulator is doing on behalf of the public, to be able to do that and to get it all out in the open. I think one of the interesting things as well is the international cooperation, as people have recognized that a fault at 3 Mile Island or a fault at Windscale affects the whole of the world. It affects the whole industry globally. So to be able to see the rigor that people go through with that is quite interesting. And when I've been dealing with regulators, you do see that community coming together to try and be as thorough as possible. John?
Yeah, I was just going to say, this period of time also marks the start of research, so more research into human factors as a subject, and then the sharing. So from the military research, the Kincaid reports that were mentioned, being shared with the nuclear industry. So there's a good deal of sharing research between different industries, which I don't know if we look at today and how well do we share our research between different industries, or are we becoming more secretive and sticking within our kind of niche areas? So I don't know if anybody in the audience has any questions around that. You know, do we share our research widely across all industries today in terms of human factors research and human-centered design?
I think while we're waiting on that, and you both may be able to help me here, does this period also showcase a consolidation of those who are involved in the supply of the equipment? Is this a time of larger, fewer firms who are building this type of plant? And because of that, is there a sense of not sharing? Is there an important competitive element that enters into all of this?
I think you're right. There's intellectual property does come into it, and it becomes a subject. And if somebody believes there is a competitive edge, it's going to influence behaviours, definitely. But I think there is also an element of a very strong element of, as a professional community, wanting to learn and understand each other better anyway. And there's good relationships there. So it is. Sometimes we've got to be careful we don't overstep the mark sometimes from our bosses, but I think the overall culture of being able to do this national show and doing conferences like this just shows that there is a good lot of learning there. For me personally, I think there's I try and drag in any learning that we can get from other sectors as well, sort of like from aviation or from rail or from chemical process. A lot of our stuff comes from chemical process anyway, and some of those systems are a lot more dynamic than the nuclear ones. When you sat in a nuclear station's control room, it's remarkable how calm and boring it is. You know, it's not very an exciting place to be once you get over the fact there's lots of screens everywhere, and that's the way it should be. So I think we can get a lot of learning there. I think the one from the 3 Mile Island is something I'm very keen on with any incident, and I think there's a really good culture there. Is if when there is an incident, we drive into it and try and get those root causes and try and find out what we can do to prevent the next one from occurring. And that is a very strong and important culture that we've got.
We've got three good questions have come in. With Grant Hudson, you mentioned the cost associated with building nuclear power plants. You could say the period that we've just heard about is where people started to think about, well, can I create a blueprint? Can I create a safe and reliable nuclear power station? And that's then where the testing and the understanding comes in. And moving through to the sharing of information, I'm trying to do this rapidly. Emily's made a great point about sharing OPEX. So where we mentioned chemical, pharmaceutical systems, any kind of high hazard, high risk systems using similar equipment, plant equipment, tanks, pipes, valves, controlling levels. There will be common OPEX that is applicable to all. So being able to share it would definitely be of importance. And then linking to Terry, I've worked on a few nuclear projects where obviously there was still issues around security, and the downloading of machine learning type data from systems is heavily controlled. So we look at, there would be benefits, but it would be the cybersecurity and the arrangements in place to capture that data. So I don't know what Andrew, what do you think about that?
Yeah, just trying to keep up with it, really. Yeah,
collecting live data.
I mean, live data is collected on reactor systems, and it is studied. But again, there's, as John was saying, that yeah, you're absolutely right. There's a whole cybersecurity element to that, and it's national security things as well can be a case on that as well. But yeah, there are things in the background that do that. Just looking. What else do we have? I'm not very good at reading and talking at the same time. Sorry.
That's okay. Yeah. I'm going to spare you that because we're about up to the hour now, so you might both get time to reflect on the questions that are there, and you might be able to reply in chat. But even my meager maths tells me that we've done 2 from 4, and we're an hour in. So let's turn now to Ned's next instalment. So John, Andrew, thanks. If you'd like to mute your cams and mics, please. And we'll now turn to our next instalment from Ned, which considers a period of crisis, challenge, and consolidation. So here we go.
And so we move into the period from the 1980s towards the new millennium. This was a period where the nuclear industry would see great structural change, privatisation of the CGB, the formation of British Nuclear Fuels, and a reduced role for the United Kingdom Atomic Energy Authority. The 1980s was a period of considerable change. The NII, more or less at the same time as the 3 Mile Island accident, published their safety assessment principles, which were intended for use by their inspectors when assessing safety cases. In 1982, for the first time, the NII explicitly recognised ergonomics and formed a working group to answer 14 specific questions of ergonomic relevance, inspired to some extent by 3 Mile Island, but also by issues observed when regulating the UK power station fleet. It was also the time when there is a realisation that the Great Britain nuclear power industry was really in crisis. The fleet of advanced gas reactors had taken far longer to build than was expected, were more expensive than expected, and each individual design was different from every other. In a sense, the people could rightly say that the entire fleet of Magnox and AGR reactors was a fleet comprised of prototypes. However, the Central Electricity Generating Board wanted to build what they described as Ford Escorts, pressurized water reactors, for the first time water moderated reactors to generate nuclear power on a commercial scale. And to do this, they had a public inquiry, the Layfield Sizewell B public inquiry, which actually lasted for 4 years and resulted in over 2,800 box files of evidence, response and discourse. The intention was that these would be, as I said, Ford Escorts. There would be a fleet of Sizewell B and 3 other identifiable stations to follow. In the course of the public inquiry, the Ergonomics Society challenged the Central Electricity Generating Board on matters of ergonomics and human factors, and at the end of the inquiry, Sir Frank Layfield had a considerable number of things to say. Human factors are of outstanding significance. Human error must be addressed in design, construction, operation and maintenance. The CGB must pay meticulous and exhaustive attention to minimising human error, and moreover the regulator, the NII, must ensure the CGB's continuing and thorough commitment. You can see some of this is shaped by the events of 3 Mile Island and the indirectly through the Kemeny Commission report. The result of this was that the CGB made 29 commitments on ergonomics and human factors, and these were summarised in a licensing, what was called a licensing activity summary programme. The Ergonomics Society, in challenging the CGB, had expended some £5,000, and Corlett and Stapleton, in a first 50-year review of the Ergonomics Society, said that the team reported they had achieved nothing in terms of wider publicity for the Ergonomics Society, and the press ignored their presentations and their press releases. That may be so, but in terms of impact on behalf of the public, it was quite profound, as will be seen. In parallel with the development of the Sizewell B design, the Thorpe thermal oxide reprocessing plant was being built at Sellafield, and just as the public inquiry was coming to an end, the Chernobyl accident happened. This picture shows you through a photographer's fisheye lens part of the Sizewell B control room. You'll note the remarkable differences relative to the Trauss-Fineth design, which by that time was some 30 years old. But how did they arrive at this design in terms of human factors? The small thumbnail at the top right shows you Sizewell B with its containment pressure dome in white in the background, and the larger grey, apparently grey, concrete block in the foreground is Sizewell A, one of the Magnox stations. So the Sizewell B design was based mainly on deterministic requirements still, although there had been about 15 years of maturity of probabilistic safety assessment. A very highly structured scheme of documentation was formulated and used, so for each of the 164 systems a set of safety functional requirements were specified, and these were then translated into system functional requirements, which culminated in a system description, the document used for the procurement of the systems from contracting organizations. The human factors team throughout the design process identified implicit human factors requirements for safety that were made in that suite of documents and made them into explicit requirements with qualitative indices for human performance and errors inserted into them. For the first time, a probabilistic safety case was being made for a new station, and human factors and human error were incorporated in that. Both technique for human error rate prediction and HART were applied to the Sizewell B PSA for purposes of quantifying human error. Although it has to be said, sometimes the probabilistic claims were detached from realities. I was involved in that design, and I clearly recall a point where we were concerned in the ergonomics team with alarm flooding, and the PSA is assuming that there would only be one alarm. So a big difference between the reality and the assumption. The NII, as the design progressed, published an important supplement, Supplement 13, which essentially said, we like the idea of PSA, but it is not the sole determinant of nuclear safety. The USA had moved more strongly towards probabilistic safety assessment. Britain was inheriting a United States design and adapting it, but it was important that deterministic functional requirements were also met. I've already mentioned the 29 human factors licensing activities. I won't describe all of them, but they were very wide and diverse in their concern and their scope. For example, checklists for guards against cognitive and conceptual error required, and these were applied in the end to guidance for management, station maintenance, operation, and indeed for the design team themselves. Task analysis of safety actions was required. Any action required for safety and claimed for safety should be subjected to task analysis, and quite separately there was also task analysis of the human-computer interfaces which were being brought to bear. Indeed, I think there were 44 different cathode ray tube displays in the control room, and that design, which was quite beyond the scale of anything in previous generations. The United States standards NUREG 0700 and 0711 were used for guiding design and assessing design, and other locally produced design guidance was produced, for example, following task analysis on the design of HCI, and human factors were directly involved in any user interface designs required for the centralized control room, and provide guidance for security, rad waste control rooms, and also local to plant user interfaces. Certain things were the subject of experimental studies. It was believed that the widespread use of mimics would improve human performance, but there were doubts about that, and experiments were undertaken to see whether the more traditional scrolling alarm lists were more effective than mimics, and the answer was that mimics were very good when a small number of alarms were being displayed, but alarm lists were the only way to deal with it when the number was larger and the problems being addressed were more systemic in their nature. The majority of the NII human factors focus was on the design, and was led by the licensing activities that were identified in the and from the Layfield Public Inquiry. The use of PSA was interesting. It showed that it was a useful tool for establishing how much really is enough, because a probabilistic case can measure the effectiveness of more or fewer redundant trains of equipment and the benefit or otherwise of additional diverse systems. And indeed, the application of the PSA did establish the need for an extra line of defence for safe shutdown. So Sizewell was very much something where human factors came to the fore, and there was a team which varied in size from 4 human factor specialists to a maximum at one time of 12. The 1990s was a period of considerable further change, but also of maturity and consolidation. Sizewell B went on to the national grid, generating electricity in late 1993, and was 1300 megawatts electrical, which compares in scale, it was enormous compared with, say, the earliest Magnox stations. The Chernobyl accident didn't lead to much change in terms of design and ergonomics, as had 3 Mile Island, but it led to an enormous growth in attention to safety culture, and considerable efforts were made in the UK and worldwide to begin to measure and assess and improve safety culture. The NII revised their safety assessment principles in 1992. They remained only applicable to nuclear power plants, but they were used increasingly by the NII for inspection of other nuclear facilities, and also by human factors people to map out what the human factors issues were that should be looked at for safety and for regulation. The majority of the Magnox and some of the AGR fleet became subject to periodic safety review, and indeed by that time some of them came into long-term safety review. And they followed very much the precedents, I think, that have been set by Sizewell. Task analysis of claimed safety actions was required, and that was done prior and informing human reliability assessment claims, scoped by PSA analysts but largely assessed by human factors specialists. And in the process of doing that work, occasional recommendations for human improvements, say, be those in training or procedural improvements, machine improvements, or human-machine interfaces occurred, but it was mostly driven by the probabilistic numbers and whether those met safety targets defined in probabilistic terms or not. In the middle of the decade, the likes of the Royal Navy onshore sites and the weapons facilities, they lost their Crown immunity and came under NII regulation, as indeed did the what was then by then the remnants of the United Kingdom Atomic Energy Authority. And there I will stop at the beginning of the new millennium for our next discussion.
Ned, great place to stop. Thanks for covering a considerable amount of ground. John, Andrew, can I invite you to join me in the hot seats? John, can I turn to you? What would you draw primarily from what you've just heard from Ned?
Essentially, we're beginning to develop methods for exploring a design from the human perspective, and we're starting to see the integration with safety and the safety case. So it's developing a need for doing human factors analysis rather than a kind of, not a nice to have, but an interesting side project. It's becoming more integrated. So Andrew's thoughts on that?
Yeah, it's. I know there was quite a lot of activity in the chat around PSA, probabilistic safety analysis, and human error performance values, and all these kind of 10 to the minus whatsits and everything. I know that can be quite contentious, but it's quite interesting to see where it came out. And I was just flicking through some of the references. If you look at the introduction to the tolerability of risk paper that the HSE have on their website, which came directly out of the Size Wellbeing Inquiry, which basically says to the public, how much risk are you happy with, guys? This is the level we're going to. We believe this is okay. So all this terminology that you see in a lot of the legislation, it's one of the informers of it, isn't it? So when you get that integration of the people with the safety case, John, absolutely, it's the full system. And one of the things here is having a number informs a decision. It's not the answer in itself. It informs the direction and decision. It's the full context. We're just saying about like qualitative analysis and quantitative, how that comes about. And if what you want to resist is that rabbit hole of going down and saying this is just a crossword puzzle and I can do it on my calculator, because that's not the case. You're missing all the expertise and judgment and value. And we're learning a lot through this period of time as well, because we're building more reactors, we're doing more work, so there's a lot more to draw on as well.
Yeah, one of the key points is confidence, isn't it? Are you confident that your safety analysis is reliable? Especially when you look at, I'm going back through previous experience where there might be a number, a risk, for the safety of the plant, and then everything's connected, and then people are looking, almost like building a jigsaw. People are looking at reliability for those individual pieces of the jigsaw, and that's where human factors comes in, because we're saying, well, actually it's a delta. I think things change. Context, scenarios can change how you think that system will operate. And I think in this period of time, human factors is beginning to get that opportunity to start demonstrating that we're not just another link in the chain as per like building a formula for the safety of the plant. But let's take dose reduction measures. How does it work? How is it installed? I'm holding back because the next section starts to really look at human-based safety claims, and we start to break down what errors are. So, but at this point in time, it's about questioning the approach, and I think both disciplines, safety and engineering design and human factors, are probably all learning from each other at this point.
Yeah, and I think it's important to note in that little brief part that the word safety functional requirement is only just coming up there for equipment, let alone looking at what people do in the system as well. So it's interesting now, these things have had to be more and more refined and defined as we go along.
And just in the chat as well, we're talking about AI There's a lot of the techniques for simulating control panels, control systems. We're talking about the use of touch screens. I did some research in my old day, 15 years ago, but looking at how nuclear power stations were designed in different countries. And for example, in South Korea, there's more confidence in the tech, in the use of software to drive through the running of the power station. So whether or not there's an appetite for that risk, and that's why, I mean, today's webinar is about the UK industry, but if you know, risk appetite has to play a part as well.
Yeah, and there's a cultural element about how much people want to trust people versus equipment as well. And even though it is the UK context, absolutely. If you look at anything, most of the technology that we're deploying are from international vendors. So that translation, especially in control room design, is very key. Yeah, definitely.
I just want to quickly pick up on Nicholas Colford's point. Absolutely, HRA for me is it's like a measuring stick. So if you do it during the concept design, you can get some confidence, and then you can identify recommendations, ergonomic improvements, and then you can revisit once those design changes have been made, and using the same measurement system, and then you've got a reliable measure. So you can then look at before and after. Have you made the system? Have you improved the ergonomics? Yeah, the debate about HRA is how it's not. There's often huge debate about which HRA method is the best method, and you know, there's hundreds of methods out there. But really, it should be, you know, stick with one, but it's how you use it, and use it twice rather than just once. But I don't know what people's thoughts are. They're all coming in. So.
Yeah, it's getting busy there, isn't it? I think a lot of it is, no matter what techniques we use, no matter what processes we use, we've got to remember that we've got to keep everybody on the journey with us, and that communication is key throughout. So some of it might be confidence, something might be cultural, something might be because of previous learning within country. You know, if a country's had a particularly bad accident because of one particular parameter, they might be more sensitive to it. So there's a lot of context going in there. But I think for me, the key thing is being able to show confidence of your own analysis and your own judgments, and keep everybody on the journey with you.
Gentlemen, I'm going to ask you to take a pause there. So thanks for those comments. And if you'd like to mute your cams and mics, please. We'll now hear the final instalment from Ned, part 4, which looks at the new millennium. And where do we go from here?
Others may disagree, but I would say that in the last 20 years since the new millennium, the industry has matured, and the application of human factors to the nuclear power industry has also matured. So where are we now? Well, Sizewell B, our newest nuclear power station, is getting on for 30 years old and has already had its first major refurbishment from original design. Generally, we have an aging nuclear power plant fleet, and some have already gone into decommissioning, and some are moving towards long-term care and maintenance before eventual demolition in about 100 years' time. However, there is also a new fleet on the way. We have Hinkley Point C already being built, and the ONR have had processes for generic design assessment for an advanced boiling water reactor, and for thus far 2 designs of pressurized water reactor, and maybe some of those will be built. Notwithstanding the fact that we've lost power stations from the fleet that was built in the 60s and 70s, and Sizewell B in the 80s, the nuclear continues to contribute 20% of the capacity for generation, which reflects reduced electricity consumption in the UK overall. Looking at safety functions in particular, there's a continued refinement and improvement of the claims that are made for human error in nuclear power plant PSAs, and they're now called human-based safety claims, HBSCs. The new human claims are largely driven by and framed by PSA and new safety cases for long-term review and periodic safety review. And the regulator ONR now expects to see human error assessment for latent errors. That's errors that might have arisen, for example, in maintenance, but only show themselves when a standby safety system is called upon to fulfill a safety function in duty. There are initiator errors where a human error could cause an accident sequence to occur. They're few and far between, but where they are identified, they seem to be largely to do with human interaction with protection systems, as well as the more traditional post-fault or Type C human errors requiring to be addressed. The important thing to say, I think, if I were representing ONR, would be these are only numbers, and the numbers only matter if they're used through assessment to drive changes in design and operation to meet the, as low as reasonably practicable, the ALARP principle, which means that human error, where it's important for nuclear safety, should be minimized to the extent reasonably practicable. Notwithstanding the fact that it's now about 30 years since the Crown Immunity sites lost Crown immunity, they are still catching up in terms of the technology of making a safety case. There are many reasons for this. I think the principal one is that with nuclear power stations there have been so many of them that the cases have similarities. Although the technologies are very different, the cases have similarities in structure and content, whereas the Crown immunity sites have much more variable processes needing to be assessed, and I think the same is also true for facilities at Sellafield. Let's look a little more at the relationship between safety functions, human factors and regulation. The ONR Safety Assessment Principles, or SAPs, were updated in 2006 and 2014. Within them there are 12 human factors safety assessment principles, 4 more concerned with management for safety that closely involve a human, and there are other human-related principles embedded throughout the remainder of the SAPs. For example, there are some to be found in controlled instrumentation and others to be found in fundamental safety assessment. The ONR have very clearly set out expectations that Type A, B and C errors will be analysed, and that is now including errors of commission. A Type A error is an error which is, if you like, embedded in the technology. It's stored in the technology until that technology is called upon to act. A Type B error is where the human actually initiates an unsafe sequence of events, and a Type C error is an error where the human is required to respond to an unsafe sequence of events, and they would fail to do so. The ONR accepts credible human-based safety claims as an integral part of their safety functional claims. In other words, the human acts are seen as a sub-function in the overall safety function from this perspective. However, that is only accepted provided that task analysis and other human factors work has been undertaken which qualitatively shows that the bases for identifying improvements in the design or the operation of the design will meet the as low as reasonably practicable ALARP and modern standards. One human-based safety claim, by the way, can contain multiple human error assessments. For example, a human-based safety claim might be that a human error 1 and human error 2 would have to occur, but there's an acknowledged dependency between them. In other words, the probability of one error occurring increases the probability of the second occurring. And it may also, as a logical alternative, include the actions or the errors for human error 3 and a recovery task to recover human error 3. So human-based safety claims can become quite complex, both in terms of the number of tasks that are included within them, and within those tasks the number of errors and the relationship between those errors that may be analysed. I'm making a quick aside at this point to try and explain in a little bit more detail what I mean by a nuclear safety function and a human-based safety claim. This tree, if you look at the second row down, there are 3 boxes. The first, fully insert all shutdown and control rods to maintain negative reactivity. Let us suppose that is an automatic function, and should that fail, that we can inject boron to maintain negative reactivity, and that is also an automatic function. However, if both of those fail, then the injection of emergency boron to maintain negative reactivity would have to be done by humans, and this human function becomes a human-based safety claim, and it's a claim to meet the overall requirement that negative reactivity needs to be inserted to ensure that the reactor either shut down or maintains its shutdown status. So in order to do that, we move into something that begins to look a bit like task analysis, that we need to establish that reactivity is rising or will rise, so indicating the need for emergency boration, and of course that will be dependent on alarms or indications. We will then need to operate controls to initiate that emergency boration, manual controls, and we will then need to check that indeed this has had the due effect by checking that the reactivity is now falling, to ensure that the function intended to be delivered has been delivered, and that of course that will be done by the observation of indications. So this looks a bit like a success tree, but the construct really is constant whether you're looking at a purely deterministic case or a probabilistic safety case, and the difference of course is whether you're making qualitative or quantitative claims on human reliability. But really this process can only be credible if it's built on a demonstration that the design is suitable for those claims, the necessary alarms, indications and controls are provided, and they're provided in a way that ensures that people will operate them reliably and in a timely fashion. So it still rests upon attributes of the interface design, the environment, training and procedures, etc. And still of necessity should require proper task analysis, and where tasks already exist, verification and validation, whether that be on the station or in the case of emergency activities in the simulator, to show that indeed the claims for human reliability and task efficiency and reliability can be properly met. And of course, now that we have so many years of operating experience around the world, these claims should also be underpinned by operational feedback, where it's a routine task from stations, or where it isn't operational feedback, ideally taken on high fidelity full scope simulators. So in terms of nuclear power, what are the challenges in the UK for human factors professionals today? Well, the sector seems set for growth. We've got Hinkley C on the way, and we've got applications, 2 of which have been ceased for a BWR and a PWR, but another PWR is being assessed to see whether it's licensable in this country even as we speak. And we have a brand new technology in the shape of small modular reactors coming along, which may, if the design intent is followed, be operated entirely remotely. Decommissioning is set for growth. How do you dismantle these to the extent that you can safely? How do you handle the waste? And how do you put the stations into long-term care and maintenance? Within the sector, it has to be said Others may take a different view, but my view is it has to be said that nuclear safety is still seen very much as an issue to be addressed by technology and not a human problem. This is reflected to some extent in ONR's safety assessment principles, but very much in the culture of the organisations which are dealing with nuclear safety. So unfortunately it sometimes means that human factors, there is too little too late, very often when that occurs in reaction to observations and findings by the nuclear regulator. At times it can be seen to be it's all about numbers, it's only really about human reliability, but as I've already emphasized, that is an emperor without any clothes unless it can be substantiated by good sound evidence drawn from either design principles in a new design or operating experience and simulator experience in an existing design. The other problem, I would say, is that we have, in that period of rapid growth that we saw in the 60s, 70s and maturity in the 80s and 90s, we have an aging human factors professions population. I'm the last person still working who worked on the Sizewell B project, for example, and unlike the 70s and 80s, where there were institutions who spent a great deal of time training people, that is not true to the same extent. Certainly if you work for EDF, they have an academy, but if you work, as many do now, in private consultancies, the centralized expertise and the time and effort investment doesn't occur to the same extent. I'm not going to offer specific commentary about the detail of this slide, but please feel free to take this away and make use of it. I have to say there's a great deal of information on the history of the nuclear industry available on Wikipedia and the World Association of Nuclear Operators. There is considerable amount of information as well. So if you look around, you will find it's out there for the taking. As I've already implied, the early years are more difficult. The industry was surrounded by secrecy, and it's only in more recent times has it become much more clear and open as to what's going on within the industry. Thank you very much for your time and attention.
Thanks to Ned for a fascinating and personal viewpoint, looking back over the last period that we've both come together on. So John and Andrew, thanks for joining again. We're into our final panel. I know you've been answering questions, comments as we've gone, so thanks for that. So I think some flexibility here then, really. It's here's a space to say what hasn't been said, or to comment on what you feel we could draw from our four presentations today. So Andrew, can I turn to you first?
Okay, yeah, no problem. It's quite interesting. You know, I mean, we've been going for quite a while now, and we've only scratched the surface of this timeline. There's a whole history in here. I think it's great to see how we build little steps all the time. Unfortunately, some of these phases have been characterized by major accidents like 3 Mile Island and Chernobyl, etc., and Fukushima in recent years as well. But we continue to learn and grow and develop. Just like any other, like aviation is very similar, and aerospace and chemical process as well. But it's good to see relevant to what we're talking about here today, which is the UK nuclear industry and how we grab that information from everywhere. I recognize there was quite a lot of chat in the last one about the unique regulatory framework that we've got within the UK. For anybody who's unaware, it's goal-based rather than being prescriptive. So that means basically there's a moral obligation on you to actually say, no, I believe this is safe, and to come up with that ownership, you know, really grab the ownership of understanding of what you're dealing with before you go into regulator. And you're absolutely right. I've seen a couple of comments here. It does depend on the person that you're speaking to and the regulator on the day as well, because I think that's a good reflection actually with human factors is you can't consider a person a machine. They're not going to be responding the same way every day, every time. And to try and quantify a person like a machine, it's never going to happen. It's never going to be, nobody's going to believe it anyway. So it's just understanding where we can all feed in and get into a good, the best solution that we can at the time. And if you really believe that as a team, when you go into the regulator, that's going to be an easier conversation if you actually believe what you're saying, if you understand what I mean. It's not the line, but you just got to really understand it and believe it. The other thing that really came out is when we talk about safety claim development. As a safety case person, I'm talking to, yes, human factors extensively, along with the operators, but I'm also talking to CNI engineers and mechanical engineers and seismic specialists, and a whole raft of people to come up with what we actually focus in on and say, okay, this element is about you getting the operations as best you can, and this element is safety, and I want to make sure I understand my margins throughout. So what I'm always keen on when we've got teams is to make sure that nobody writes a safety claim without getting that understanding from that multidisciplinary team to really focus it. And that's why in the introduction I said, when I talk about leading cases, it's always multidisciplinary team. It's whatever's relevant for that one. So yeah, that really stood out at the end for me.
Just on that very point, Michael Harrington's mentioned, obviously the opposite. We talk about a prescriptive regulator, and you wouldn't be able to have the debate. So by having different ONR inspectors, different personalities, different approaches, you can put forwards with a goal-based system. You can put forwards your evidence and your opinion and your conclusions on the safety of the system, and then there's a period of discussing why you think that something is a certain way. Whereas if you go down the prescriptive route, there might be less rigor. So it could just be assumed, almost not tick box, but I'm just finishing off a video for the conference where essentially design standards are kind of like show you the door, but they don't show you the rest of the way, take you the rest of the way. One thing I'm keen on seeing more of in nuclear is more kind of research. I think Terry mentioned gathering machine learning and data. So more gathering of human factors data research using some of the modern systems that are in place. So we've got really easy to build a simulator now. I can run a simulator off my laptop. The software is out there. We can run through. So at the kind of GDA or development stages, we should be doing more kinds of hands-on research and building up a much better picture of how people will be using the facility. So I think that's what I've drawn from this. Looking back through the last four videos, some of the work that Reg Sell was doing in the late 60s, early 70s. They were doing, they were building mock-ups, looking, simulators, looking and understanding how people will interact with their design. Now, if we're changing what the design looks like, so we're changing affordance. I think Bill mentioned the use of touch screens. I don't know if people will be familiar, but the 10-inch rule for the design of touch screens, I come across CNI engineers who say, well, the standard is 10 inches. And they essentially, you get into these huge debates where you have to say, well, actually, the technological solutions that exist in the marketplace now are 15-inch or 20-inch, or and I find I'll actually model up how model up what it looks like with real pieces of equipment. So make, model, manufacturer, cost, delivery date, so you can actually, make it more tangible with a lot of the modern use of 3D and digital modeling. I'm just going to go back to the questions.
Yeah, I think there's a couple of interesting ones about the regulation there. An interesting thought there from Grant, and just a little bit after as well from Dave. I think it's quite interesting, the exposure to how the regulator thinks within supply chain, because not everybody gets an opportunity to do regulatory engagement or direct work for the regulator. I think that's actually quite an interesting comment, because the regulator will be keen, from my experience of working with them, is how else do they understand what the industry is doing? The industry is not just a nominated set of people from a set of licensees. It's all of us contributing together and that greater learning. So I think that's an interesting thought about understanding the regulatory process and thought process, not just a procedure, but the thought process within supply.
I just want to
Not sure about the AI though.
Yeah, AI. But, I want to pick up on Emily's question. How can we facilitate more learning from this kind of experience? So when Ned has mentioned that there's an aging HF design experience, we touched upon the EDF Energy Academy, and I know in North Wales they're developing something called the Nuclear Futures Institute. So I think allowing people to work together on a common goal or a project, that's a muse. So it's not it's not confidential. It's not a client's kind of secret project. But if we come up with some generic, let's design a generic control room, and then allow people to volunteer their knowledge, their experience, and just kind of build up either through webinars or online tutorials, but allow people to share their war stories, share their lessons learned throughout their career. I think hopefully that will go some way to some kind of knowledge elicitation. But back in my Airbus days, if once operators, this is like Logan's Run, once the operators reached a certain age, they became tutors, they became mentors to the next crop of apprentices. And whilst I was there, I saw that they removed that. They removed that process, and we saw a reduction in quality and an increase in injuries on the shop floor. So making sure that there is some kind of formal process for passing on the knowledge. I just think maybe with the Chartered Institute, we need to develop a vehicle for doing that. But great question on that.
Well, I think on that point, I think let's just underscore that we'd certainly like to see the nuclear sector group that you can reach via our website, ergonomics.org.uk, get involved, nuclear sector group, and that will lead you through. So if you'd like to play a part in the future in what this group does, considers, influences, then that's the route to take. I think also useful here perhaps to say, given that we've a maximum of 10 minutes now to run, although the chat will be open until 10 minutes from now, is that there are 2 more events planned by the Nuclear SIG in October and November of this year. So plenty of time, a good deal of scope to think about things and to get involved. So if you've been interested in what you've heard, then now's the time. So I'm just going to take my facilitator's prerogative for a second with you two and say here we have an industry not too far away, at least in its inception, from the military, a sector in which we see a mandatory use of human factors Are you surprised that hasn't happened in the nuclear sector?
Yeah, it's sorry, John, Andrew, are you going to answer?
No, you go for it, John. I'm still collecting my thoughts, really.
They're mandated. So you mentioned we've got the other talks. So the second webinar is about nuclear decommissioning, and then the final one is kind of the future of nuclear, and then our role within it. So looking at use of artificial intelligence, possibly small modular reactors that are being remotely operated. So I've not ducked the question. Going back to the question, within the military, there's always that history from post World War II, early days of the Ergonomics Research Society, and lessons learned from World War II, and in communication. Nuclear is very secret, so that high level of secrecy, opaqueness, has kept with it. So where we've got, I guess, there are an awful lot of nuclear regulations and standards, but going from the standard and applying the theory in practice, and then being given the budget, the time to practice human factors, I think is where the battle is. So I don't think there's an argument about the theory and the benefit of human factors. The battle line, or it is on fitting it into kind of complex programs. So I didn't want to bring this in, but I will. That agile management now is being, there's the waterfall management where you have this sequential flow through. You'd be given a program, an organogram, kind of, you knew who was who, you knew who to talk to, and and the activities were all set out. That made it easier to integrate human factors, because you could see the design stages, and they often were in serial rather than parallel, and you could then identify where the key stage design gates were and feed in. There has been a move towards agile in the nuclear industry, and we're now in a situation where there's lots of parallel working going on, and in order for ergonomists or human factors practitioners to keep up, we would kind of have to find a common model, or a common, whatever this moving feast is, that is the design, we have to somehow get hold of it. And that's where I think with defense is a much slower industry in the development. I mean, you're probably still using probably still saying, I don't want to talk out it, probably still using waterfall, and it's probably more of a mature process. But I'm seeing nuclear now is more influenced by kind of financial return on investment. I don't know what Andrew thinks about that.
I'll wait for the post bag to bulge on that one, I think, John. So Andrew, turning to you.
Yeah.
Yeah. Well, I'll see if I can open any more can of worms there. Hey. Yeah. No, I think it's quite interesting when we talk about the nuclear industry. You can look at it as one amorphous lump, if you want, or you can look at it as a defense industry, a power generation industry, a chemical process industry, and they're very different. You won't be talking about a military application alongside, say, coal-fired power stations, and yet it's quite a broad spectrum that we deal with. So yeah, in some of the processes, in some of the military ones, they are more, they are more procedural. They are more, by the book in terms of what's expected. A lot of them aren't. I think there's a lot of benefit that people have seen to see modern engineering processes put in place. The Felgate processes that were up at Sellafield for many years, or similar ones, the gated processes and design processes that have been put through on the there's various standards around that, isn't there? I think for make you feel better, it's not just human factors that struggle to keep up with this moving baseline of design. All the disciplines do, because everybody's just like paralleled up to try and get these major projects done, and it's just so I think on one job I had 22 work fronts on the safety case running in parallel, and how do you keep up with all that? It's unbelievable sometimes. I walk into NewGen one day and you think you were going to deal with a problem on electrical supply, and you're actually dealing with under decommissioning plan or something like this. So I think it's a problem we're all struggling to deal with, especially with technology adding in another parameter in here. And sometimes you can't fill in your emails because you find Outlook's already filtered them for you. No, I want to be the one who prioritizes my work. Thank you very much. And sometimes I think, where's the human factors in the project development? Because it's the errors, the latent errors that you can put into a design because everybody's in this like chaotic environment could be quite significant.
Yeah, and it has been. There's a paper, Ironies of Automation, which looks at latent errors in the design process. And that one key, I mean, just from previous experience and my own opinion, I've worked in project management teams that are set up around discipline. So you find that all the Gantt charts are set around EC&I to deliver EC&I stuff, and safety to deliver safety stuff, and human factors to deliver human factor stuff, and so on. And then I've worked in projects where it's a systems based or goal based, and they're multi-discipline teams working on the design of a system, and the difference is noticeable. So it's another webinar to talk about the human factors of project management and the influence of project management on successful design. What my kind of sort of final thoughts for this is just that we should be having this conversation, so out in the open, talking, not being on your own and kind of stewing over it, but being able to talk about it, and the answer will be in there somewhere.
Okay, I think that's a positive note on which to draw things together. We, by the Institute, as you can see, are very happy to facilitate further discussion in the forum that Tina helpfully outlined earlier in the chat. So if you've any doubts as to where to go, the chat will let you know that. My thanks to Andrew and to John and to Ned for emphatically scratching the surface on a topic that we knew would go beyond its boundaries, but it's now that we must close. So just to underline John's remarks, there are 2 more webinars to come in the year, in October and November. If you'd like to do something before that, get in touch with the sector group. Keep your interest going, and we'd very much look forward to seeing from you again. Just as a closing remark, I think we've illustrated today what a fascinating career human factors can be in a sector like this. If you're interested in becoming a human factors specialist or changing careers, the Institute are running a fascinating day tomorrow on careers in human factors. Check the website for that. And our next appointment here on our online platform will be regarding a familiar subject of healthcare. And that'll be happening in the middle of March, where we consider the impact of human factors in a number of areas of the healthcare sector. So again, the chat room will remain open for a short while, where you can say goodbye. We will look forward to see you at a future presentation. My final thanks then to Andrew, thank you, to John, thanks, and to Ned. We look forward to see you both in the future. Thank you and goodbye.
Thanks everyone. Are we staying on for any questions? Further
Not too sure. Still on air, apparently.
questions? Yeah.
Yeah. Stephen has switched us off yet.
We can stay. We can stay on if you want.
Okay.